Yes, so without further ado, so today we have Victor Luis Espinoza, based in the Federal University of Santa Catarina in the south of Brazil, telling us today about the genericity of singularities in spacetimes with weakly trapped submanifolds. Victor, if that's okay, let's try 50 minutes plus discussion.
I think it'll be fine. 50 minutes. Yes. Okay.
Perfect.
So
please go ahead.
So let's start. So first of all, I'd like to thank the organizer of this event, especially Professor Paulo Piccioni for the invitation to present this work. So today we'll be talking here about my paper, which was done in collaboration with Professor Ivan Pontual, entitled On the Genericity of Singularities in Spacetimes with Weakly Trapped Submanifolds, published March of this year. So first, to motivate our investigation, the singularity theorems, for example, the ones from Hawking and Penrose, they are well known to give us conditions for singularities, that is, incomplete and extendable causal geodesics, as to exist in spacetimes with reasonable physical and geometric assumptions. So, a question that might arise is, are the conclusions and or assumptions in these theorems stable under small perturbations of a metric? So if you slightly perturb metrics, do they remain the same, right? Are they stable? So this topic was explored by Garak, Lerner, Bean, and other mathematicians and physicists. Another question, so how frequently, at least in a suitable class of physically interesting spacetimes, do we expect singularities to happen? So we want to start, at least give a partial answer to this second question. So there are some previous studies about these topics. So to cite a few. Here, Lerner introduced the space of Lorentz matrix over a non-compact manifold as a topological space using the Whitney topologies. The genericity of the so-called generic property in spacetimes was explored earlier by Bean and Harris, and later in a more complete manner by Larson. Recently, we have a paper by Schruschel and Galloway, where they proved a density theorem for error-trapped surfaces near a MOTS, a marginally error-trapped surface, within the setting of initial data problems. Okay, so the proposal of our paper is, so on the first part, we'll give a generic property, which is actually we call a prevalence property, which we'll define precisely soon, relating to singularities of spacetimes containing weakly trapped submanifolds using Whitney topology methods. And on the second part, you want to give a similar statement as of Schruschel and Galloway, where they talked about density, but now we want to talk about genericity on a suitable Banach manifold. So first, the first part, we start with stability, genericity, or prevalence to be more precise, and singularities. So first, some preliminary ideas just to establish terminology and notation. So first, let X be a topological space. A subset A of X is said to be residual if it contains a countable intersection of open dense sets. And a property of elements X is said to be generic if the set of all those elements that possesses such property is residual. So this is what we mean by a generic property. And the complementary notion of residual is meager. Now about prevalence. So again, in a topological X, a topological space, and C, a closed subset of X. We say that a subset A of C is prevalent in C if C minus X, removing C minus A, is a meager set in the larger space in X. If C minus A is a meager set in this Yes.
So just a quick question. What are you trying to cover with a residual, which wouldn't be just, open dense set? Why do you need to allow for countable intersection of open dense sets?
We actually don't here, but this is just the standard definition of a generic. Right, so we'll allow it. We'll allow here to cite the larger the definition, right? But a open dense will be residual, right?
Yeah.
Yeah. So it's just a definition, right? So but at the end of the day, for what we obtained is open dense.
All right. Thanks.
Right. Okay. So the prevalent set here is meager. Is the set A in C is prevalent. If C minus A is meager, C minus A is meager in the whole set X. All right. So we have here this straightforward topological proposition which we used a few times. So for C closed A, if U in C, if the set U in C is open in X and satisfies the interior, the relation, the interior of C is contained in U, then U is prevalent in C. So item A here gives us a condition for a set to be prevalent in a closed set, a set to be prevalent inside a closed set, and this is frequently used in our paper. And B, item B, if C is a bare space in its subspace topology, then every residual set of C, that is residual in its own subspace topology, is prevalent in C. So item B tells us when a residual set is prevalent, at least for the situations we're interested here. Okay, now the converse of B is false. So here I give a simple illustration. The set C on the plane, this is all on the usual R2 plane. So on the plane, C is a closed set. It is the union of this vertical line with the closed half space. So C is closed, therefore a bare space in the plane in its usual topology. U is the open half plane, right? Now, if we consider C minus U become the union of these two lines. These two lines are meager on the whole plane, on the whole R2 plane. So U is prevalent. So U is prevalent in C, but C minus U is not. C minus U doesn't have C minus U is not meager in C, right? Because in its topology, this line will contain open sets, right? So it can be meager. So the converse of B here it doesn't work, right? It's not the condition is not equivalent, unfortunately. So now to fix our more geometric setting, fix M a smooth, connected, and non-compact manifold with a boundary of dimension m plus k. Sigma a regular submanifold of codimension k inside M. We denote here gamma R of L, the space of CR Lorentz matrix over M. That is the CR sections of the Lorentz bundle L projecting to M, where here the regularity can be either finite or smooth. We topologize the space of Lorentz matrix with the CS strong Whitney topology, where S is less than or equal to R. Now, some previous results about the space of Lorentz matrix due to Lerner. First, fix X, a nowhere vanishing vector field over a manifold M. The subset of CR matrix for which the vector field X is time-like, where here denoted STRX, that is the CR spacetimes associated with X, this set is open in the C1 topology. Now, notice that all metrics in the set are time orientable. The set SR sigma is a set of metrics for which our submanifold sigma is spacelike to such metrics. This set is C0 open. And CSR, the set of stably causal metrics, the CR, stably causal metrics, which is also C0 open. Now, so yet a few more important sets. The set SER is the set of strict time-like convergent metrics. That is, the set for which its Ricci tensor is strictly positive on causal vectors. These conditions, the metrics satisfying this condition are said to satisfy the strict time-like convergence condition. And analogously, ER is the set of satisfying the usual time-like convergence condition. That is, the set for which its Ricci tensor is non-negative on causal vectors. Now, Lerner shows that SE, the set of strict time-like convergent metrics, is C2 open. The set of time-like convergent metrics is C2 closed, and the closure of SE R is contained in E. Moreover, we have this theorem, and this is a proposition by Lerner, which here I have reinterpreted it in our notion of prevalence. This states that the interior of the set of time-like convergent metrics equals the set of strict time-like convergent metrics. And also, as a consequence, the strict time-like convergent matrix is prevalent in the set of time-like convergent metrics. So these are early established notions. Now, to begin with our main results. Now here again we fix sigma, a submanifold or codimension higher or equal than 2. Sigma is closed, that is compact without boundary. And we also fix X a nowhere vanishing vector field over M. The topological space under consideration here, our X topological space, is the set of CR matrix, that is the intersection of the sets I introduced earlier, that is STX, intersection of STX, S sigma, and SC. Now, in plain English, so this is the set of stably causal, time-oriented by X matrix, and matrix for which sigma is spacelike. This, since all these properties are open, this set is open in the space of Lorentz matrix, is C1 open. All right. So this open set is the background space I will be working here. Now, denoting by H of G the mean curvature of sigma for the associated metric G, we denote by a slant A the set of metrics for which sigma is a future trapped submanifold. And analogously, by FA, the set of metrics for which sigma is future weakly trapped. That is, here, this means here that where future weakly trapped is, we change the strict inequalities on the weakly trap definition for non-strict ones. Now, we show that we can easily see that A is C1 open and FA is C1 closed. Moreover, adapting the topological techniques introduced in Lerner's paper, we can also prove that in the C2 topology, FA equals the closure of A, and also the interior of A equals FA. In particular, as a consequence, A is prevalent in FA. So in the sense of prevalence, it means, right, in that sense of almost all, right, almost in the sense, almost all weakly trapped submanifolds are actually trapped submanifolds. The set of weakly trapped submanifolds which are not trapped is small in a topological sense, at least. Now, just as a remark here, I cited this result for C2, but it is straightforward to change our proof in order to adapt to CR or even smooth topologies, metrics and topologies. Okay, so now to work our first main theorem, we fix the codimension of sigma to be 2. And we can assume on metrics to be smooth, not a finite regularity. For simplicity, I assume them to be smooth. So here we denote by slant m the set intersection of A and SE, that is the set of strict time-like convergent metrics for which sigma is future error trapped, which then C2 open, therefore smooth open, and Fm the analogs, but for Fa weakly trapped G matrix for which sigma is weakly trapped, and G satisfies the time-like convergence condition. This set is closed. Now, due to the previous results relating E and SE, also A and Fa, one can see that the interior of Fm equals M. Thus, again, as a consequence, M is prevalent in Fm. So again, in our topological sense, almost all metrics. Now, sorry. Now, G in M. Notice that all metrics G in M, they all satisfy the Hawking-Penrose singularity theorem. So they all have singularities. So now, since M is prevalent in Fm and all metrics in M satisfy the Hawking-Penrose singularity, in a topological sense, almost all metrics in Fm have singularities. Summarize this discussion. Here I cited yes, Professor?
Can you maybe give us an idea of what the Hawking-Penrose singularity theorem states?
Sorry, you want me to remind?
Yeah.
Don't remind it. Don't completely remind the statement of the Hawking-Penrose singularity theorem, but it has I can cite a light version of the Hawking-Penrose theorem. It states that if, as it says here in the second part, if sigma is future trapped, if our space-time has a future trapped codimension 2, which call surface, right? So if it has a future trapped surface, if it satisfies the time-like the strict time-like convergence condition, and is actually I believe you can. I said here stably causal, but I believe we only need causality. So in this, with these three assumptions, a weaker version of the Hawking-Penrose singularity theorem states that under these three conditions, the space-time Mg is causally complete.
Can you remind me what's stably causal?
Sorry, stably causal?
Yeah.
Yeah, I believe it can be. You want me to remind what stably causal is?
Yes, please.
Yes, please. Okay, so a metric is stably causal if you can slightly perturb it,
These perturbations are also causal.
Yes, I was going to say exactly that. Essentially, right? The perturbation is in the Whitney topology, to be precise. Your audio is breaking a lot. Paulo. Sorry. Okay, Professor Henrique?
Sorry. Just causality means.
Oh, causality means?
I think people in the audience might not be immediately familiar with general relativity vocabulary, that's all. So if you can clarify some of these terms.
Okay, so we say that space-time is causal if it doesn't have time, it doesn't have causal loops, right? If there are no causal loops, there are no curves, loops, which are either time-like or light-like, right? If this doesn't happen, we say that our space-time is causal. Essentially, it's not precisely like this, but you can think that you can go back in time in a causal space-time. Either a light, matter or light can go back in time.
Okay. And then it's stably that if a perturbation of it is actually causing it.
Yes, exactly.
I see.
A C0 perturbation.
I see.
Yeah, C0 perturbation. It's a perturbation, the C0 topology. The topology that we're working here, the Whitney topology, if perturbing in this manner, it stays causal. Then the metric is stably causal.
I see. And the existence of an incomplete causal geodesic, what kind of statement is this? So it appears the emphasis is on the incomplete.
Complete, yeah, it's incomplete. It's not. You can't be infinitely extended, right? It eventually stops. You can see a geodesic cannot be extended indefinitely. A causal geodesic, a time-like or null geodesic, a light-like null geodesic can be indefinitely extended. You eventually stop.
Right. I see.
Okay, so just so this theorem here is as stated in our paper, all right? So allow me to just read it. We let Mg be a space-time of dimension higher or equal than 3, where G is smooth and contains a space-like closed surface sigma. A surface here is a codimension 2 submanifold. Just also a general relativity terminology. Assume the following holds. Sigma is weakly future trapped. G satisfies the time-like convergence condition, and Mg is stably causal. Then there exists a prevalent set X in Fm such that if G is an X, then there exists a net G lambda of smooth matrix on M such that G lambda converges to G in the smooth Whitney topology, and such that for each lambda, the associated spacetime M G lambda satisfies the following conditions. Now sigma is future trapped. G lambda satisfies the strict time-like convergence condition, and Mg is stably causal. So applying the weak Hawking-Penrose theorem, we also conclude that Mg spacetime Mg lambda is causally incomplete.
So does that allow you to completely complexify the weak, the weak guys, everything you need to complexify?
Anything needs to? The audio was a bit.
I'm saying it appears it looks like a compaxification result, right?
Yeah.
It's kind of saying that the only thing at the boundary of the G lambda fellows is weakly future trapped.
Yes.
Is that, am I right to understand this? This is the compact.
I haven't really thought about compactification. It could be actually. As it has an interesting point. We haven't really thought about compactifying anything.
I see.
I'm not sure, but that's I want me to take a note here. I'll think about it later. That's an interesting point.
Cheers.
Compactification. Okay, thank you, Professor Hicke. All right, so now this is a statement for codimension 2. We wanted to think about if you could obtain some analogous for higher codimensions. Now, for higher dimensions, we need a better control, not only of the Ricci tensor, which was essentially what we were doing there with the sets E, but also a finer control of the Riemann curvature tensor. All right. So, and this control here is it ends up being slightly more technical. So let us consider the set, which we call here P, the set of C2 matrix, where its associated Riemann curvature tensor is strictly greater than 0 on this combination of vectors here, W, V, V, W, where all V are causal and W are non-collinear to V. Oops, sorry. And FP, the analogous, right? The non-strict analogous. Now we can show analogously that P is C2 open and FP is C2 closed. And also, as before in the C2 topology, the interior of FP equals P. So as a consequence, P is prevalent in FP. Now we can relate this PFP with a more friendly set, a more friendly notion of the tidal force operator. So the tidal force operator as given here. The set O is the set of matrix such that it's the associated tidal force operator as described here is these both versions for time-like and for light-like vectors. These both versions are both positive semi-definite. Right, so this is O. If this both these operators for the time-like and light-like case are positive semi-definite, the metric G is in the set O. Now one can see the following inclusion relations. P is in the strict time-like convergence matrix, and also this multiple inclusion here. P is in O, the set for positive semi-definite tidal force operators, which is contained in FP, and all of these are contained in the set of time-like convergent matrix. So as a corollary of this multiple inclusion here, actually O is prevalent in FP. Okay, so to obtain an analogous result for hierarchical dimensions, here we need a singularity theorem for hierarchical dimensions. Now, an interesting one that exists is a theorem due to Galloway and Senovige. Now, in our case here, this theorem is slightly more technical. I don't recall the statement, but one extra is similar to the Hawking-Penrose, but it requires a control also of the curvature tensor. So in our case here, having a positive semi-definite tidal force operator along causal directions fits in the conditions of this singularity theorem by Galloway and Senovige. Right, this is the important part here. So now we follow again the same steps as the codimension 2 situation, and we denote slant A is intersection of A and P, which is open. FP, it's closed analogous, and then we introduce slant G to be the intersection of A and O. Again, the interior of Fn equals N, and N and G, and the set G is in between N and Fn. So therefore, G is actually, N will be prevalent in Fn, but more interestingly, G is also prevalent in Fn. Now, all of the matrices in G, they satisfy this Galloway-Senovige singularity theorem, so they are all singular. So they all are geodesically, causally geodesic incomplete. So we can restate a higher codimensional version. The statement is pretty much the same, but now the only thing that effectively changes is the condition 2 here. In the codimension 2 case, we had the time-like convergence condition. Now we have substituted it for the condition on the human tensor, which is slightly more technical, but it is what it is. So under more technical restrictions, we were able to obtain a analogous statement for when our space-time has a weakly trapped submanifold of codimension equal or higher than 3. All right. So that first part was our first, or in the order, that was the part involving Whitney topologies and considering the space of matrix as a topological space. Now for the second part, we changed the approach a bit, right? So to obtain a genericity result on a Banach manifold in this context of initial data and MOTS. Okay, so a few preliminary notions again to establish a notation. So an initial data set SHK, where the pair SH is a Riemannian manifold and K is a symmetric zero-dual tensor field on S. This is what I mean by a initial data set. Now, given such initial data, we define over it a function rho, a smooth function rho, and a one for J, one form is smooth, one form J, which are called respectively the energy density and energy momentum current associated with this initial data. They're given by these relations here, where here scal is the scalar curvature associated to the metric H. The norm here is the tensor norm over, and the norm here is the tensor norm over H. And div is the usual divergence, right? So this terminology here is also motivated from general relativity, energy density and energy momentum. Okay, so there is a very important theorem due to Choquet-Bruhat and Garak, which states for vacuum initial data, that is a rho and J are 0, the Riemannian manifold SH can be viewed as an embedded space-like hypersurface with K its second fundamental form in a uniquely maximal globally hyperbolic vacuum spacetime. Okay. So in the initial data setting, we define here what we mean by a marginally error trap surface. So let's SHK be a initial data set and sigma be a two-sided submanifold of S. Where being two-sided, here we fix nu, one of its two normal vector fields. We define the outward and inward nu expansion scalars, that is the theta plus and minus, respectively, are then the trace of the tensor K over sigma, plus or minus its mean curvature scalar of sigma in the direction of its normal vector nu. Now, if theta is 0, if theta plus is 0 over sigma, we say that sigma is marginally error trapped, abbreviated to a MOTS. Now, notice here that if in the case of the trace of K being 0, a MOTS is essentially a minimal surface, right? So it's just the scalar curvature equals 0. Now, a MOTS has a stability theory associated with it. So it has a stability operator as given here, this L operator. It is rather lengthy, but its key aspect is that it is a second order linear elliptic operator, right? It is its main property for us here. It is an elliptic second order linear operator. Now notice also that if we make this x here in the definition of the stability operator to be 0, we essentially recover the minimal surface stability operator again. So there is a parallel with MOTS and minimal surfaces. Professor Ivan, who worked with me, knows a lot more about the parallel between MOTS and minimal surfaces. I only know the very basics. So, continuing here, theorem. Sorry. So, what we have here is a theorem that states a some spectral properties of the MOTS stability operator, right? So, first, there is a real eigenvalue lambda1 called the principal eigenvalue. It has the property that for any other eigenvalue mu, the real part of mu is higher or equal to lambda1, and its associated eigenfunction is unique up to a constant and can also be chosen to be strictly positive. Secondly, the principal eigenvalue is non-negative if and only if there is some smooth positive function psi such that L evaluated at psi is non-negative, and the same holds for positive, and the analogous holds for positive principal eigenvalues. So this theorem here, I forgot, is due to Anderson, Mars, and Simon, and also Galloway. Okay, now we also need, since we want to eventually talk about singularities, we need a singularity theorem for the situation here as well. So to state it, we say that for a connected sigma of codimension 1 inside M, we say that inside S, we say that sigma separates S if S minus sigma is not connected. We then write S minus sigma as this disjoint union, S plus and S minus, where S plus minus are open submanifolds of S. So a useful singularity theorem for this situation is one due to my collaborator, Professor Ivan Pontual, which states let M n plus 1 G be a globally hyperbolic spacetime which satisfies the light-like convergence condition. So let Sn be a space-like Cauchy hypersurface, and sigma or n minus 1 inside S a connected compact MOTS without boundary separating S as I've defined it above. I also assume in this case that in the separation the closure of S plus is not compact. Now, assuming also that the principal eigenvalue for the MOTS stability operator of sigma, assuming this is non-zero, then the associated spacetime Mg is non-geodesically complete. So I try to make a bit of a draw here. So the idea here is, right? So since we're assuming our MOTS stability operator that principal eigenvalue is non-zero, the associated eigenfunction can be strictly positive. We call it the principal eigenfunction. So we use this to rescale the normal vector field of our MOTS sigma, and with this we can deform our MOTS sigma to become error trapped. That then, together with our other hypothesis here, we'll then be able to conclude that Mg is indeed null geodesically incomplete, is incomplete on light-like directions. Okay, so this is the singularity theorem for this part. Now, since we want to work with Banach manifolds, some analytical machinery is needed. So what we've done essentially is we adapted some results from this cited work here by Biliotti, Havaloyas, and Piccioni, making some slight modifications to fit our needs. So considering then X a Banach manifold, Y a Hilbert manifold, and A in the product manifolds an open set, V a Hilbert space, and F from A to V a CK function. Now, as a first proposition here, this proposition here is This proposition here, it only is used here to establish what we have called the condition T here. This condition, it became a technical condition in this paper, right? Is a technical condition which can be reinterpreted as a transversality condition. Now, in finite dimensions, it will be a generic condition on the space of functions, thanks to transversality theorems, right? The tone transversality theorem. But in this context, in infinite dimensions, it wasn't clear to us how or even if it is possible to extend such genericity transversality theorems to the situation of Banach manifolds. So since we couldn't do it, we had to maintain this hypothesis as a technical condition, which we call the condition T. All right. Now the main abstract functional analysis theorem here is the following, due to Piccioni et al., as mentioned earlier. So this theorem gives us natural conditions to evaluate genericity. We have slightly changed it from the original source, but the main I would like to especially emphasize here, item 3. Item 3 has assumes that all associated Banach manifolds, Banach Hilbert manifolds and spaces are separable. This assumption is important, right? Because we want to we're essentially using the Sard-Ismail theorem. So separability is a key assumption here. Now here let us fix again a manifold S of dimension n, and sigma. Now sigma is another submanifold of dimension less than 1 than of S, and S a closed, that is compact without boundary manifold. So what we need is to translate translate that function of the abstract functional analysis theorem from the past slide into our geometric setting to make this bridge between the this abstract functional analysis and our geometrical setting. So here the idea is X will be the space of vacuum initial data sets denoted by IDS. Y will be the space of embeddings from sigma to S. V a suitable Hilbert space, and F will be our positive null expansion scalar, which will assume to be now a function from the product space of vacuum initial data and the embeddings, right? And they will have this function form of being the trace of K composed with psi plus the mean curvature scalar, in the direction, in a normal direction of the embedding psi. Now, also to be workable here, we'll assume S to be orientable and asymptotically flat. Now, manifold structures for the space of initial vacuum data sets over such manifold S have been studied. Now, I cite here, for example, Schruschel and Delay, and also Bartnik. Now, for our purposes, we've chosen the Bartnik-Hilbert manifold structure, which is locally H2 times H1, so it is separable. For the space of embeddings, here we follow a Hilbert structure due to Alias and Piccione, where we consider a class of regularity less than smooth, but that densely contains smooth functions and can also be continuously embedded into functions into C2 alpha. Right, and to make it a concrete set, you can see we consider embeddings of class HK plus 2. Such class can be continuously embedded into a CR alpha for all R alpha and K satisfying this relation. This relation coming from Sobolev embedding theorems. And in our context, the Hilbert space will be the H space of HK functions over our compact manifold sigma. Now, theta plus here we need to now the domain of the domain of theta plus to be a workable domain needs to be there's a bit of technicality to define this domain well, but such domain can be defined, right? It will be a suitable neighborhood of the product manifold of vacuum initial data and the space of embeddings, right? It will be a suitable neighborhood around a fiducial MOTS initial data, that is a initial HK0, H0, K0, psi0, where psi0 is a MOTS inside this for this initial data. We'll call such triples, which will appear frequently, a MOTS triple for short, right? So theta plus will be well defined on this suitable neighborhood, and will be functionally it will look like this, right? As I said before. Now, one can compute the partial derivative with respect to the varying the embeddings, right? This partial derivative can be computed, and it turns out to be the MOTS stability operator as before, right? When you compute this derivative, when the triple here is a MOTS triple. Now, when you do this computation, which again it's very lengthy, but when done, you will obtain that it is the MOTS stability operator. Now, I think, sorry, Professor Henrique, I will cross the time, maybe 10 minutes. I hope that's not a problem.
Do you think you can drive us a punchline, say, in 5 minutes?
5 minutes? Yes, I have some lengthy theorems. I won't be reading them though.
Just yeah, if you can focus on some punchline, maybe in 5 minutes, that would be great.
Okay, sure. So here I've cited this theorem here. It is just to say that this is a theorem for elliptic partial linear differentials of second order of this given form. What matters is that the MOTS stability operator has this form. So the conclusion of this theorem states that such operators are Fredholm operators, which is also a needed hypothesis in the abstract functional analysis theorem. So the idea is now, with all this in mind, we can now conclude with all this list of properties well defined, well posed, we can conclude to a genericity of singularities. All right. So here, just a MOTS triple is just said to be non-degenerate if the associated Motz stability operator has non-principal eigenvalue. We say that the stability operator is non-degenerate. Now here, the first main theorem we have obtained here states that at least around assuming out the T condition here appears, as I said, it is a technical condition that remains in these theorems, but with the T condition, what it says is that around a fiducial initial data vacant set, we find a generic condition, right? So the set G here is open in the space of vacuum initial data sets. This set here, the property here states that in O, for initial data sets in this open set O, every Motz inside every Motz, the properties, every Motz in the initial data HK is non-degenerate. This property is residual in this open neighborhood O. So we have here a residual property stating that every Motz in HK to be non-degenerate is a generic property in this open set O here. Now, a problem is that we say that if it has a Motz, then it is non-degenerate. But we can't really guarantee that such Motz exist, right? So this was a problem that we faced. We thought we were done with that first theorem, but eventually this problem appeared, and we have to fix this. We had to fix it. So essentially, we need to make two assumptions. Either we start with the Motz triple being non-degenerate, then we conclude that actually in this case, non-degeneracy for Motz is actually stable. Not only generic, it's stable, which is somewhat to be expected. If you think a little about it, the non-degeneracy is associated to some positive conditions on the spectrum, so you can't expect it to be non-degenerate, to be stable. Now, in the case that the triple is degenerate, then we need to work a little bit more. So we need to restrict S further, right? This restriction comes from this theorem, which I have cited here, due to Anderson, Eichmar, and Metzger, right? So restricting the dimension and topology of S, and following this theorem, then the condition here 7 is actually open. It's what the main point of this theorem, right? So with this condition being open, we can find an open set where all such Motz we saw such initial data have Motz, right? So we have worked around that earlier problem in either case. So either the triple is or is not non-degenerate. We were able to come around it, but if it's degenerate, there is some more strict. We need to make a few more technical restrictions. All right. So as I said, now to finish, a last restriction. All right. So allow me 3 minutes, please. Let's finish. We can further restrict A0, the domain of the scalar, the theta plus, this null scalar expansion, right? You can restrict it so that all pairs HK, so that's psi, so all embeddings psi separate S, right? Then HK psi in A is a non-degenerate Motz triple. So by that singularity theorem of earlier, its maximal Cauchy development is then causally incomplete. Right. So summarizing, under 1, causal incompleteness will be stable around an open set of a fiducial initial data, and under 2, causal incompleteness will be actually generic around it, at least in an open set around a fiducial initial data. Right, so this is the big theorem. I won't have time to read it, but it's all the technicalities of the last conclusion here. And to finish, just a comparison of our two methods. right? So the advantage of the first method, first, it requires only stable causality, and second, it is a actual space-time result, right? So the second method, when we need a space-time associated with initial data, with vacuum initial data, this space-time will be a globally hyperbolic. So the causality is a lot stronger than stable causality. And however, in the second method, now initial data methods are frequently fairly used in applied and numerical general relativity. So I mean, we believe it to be interesting to also have a initial data results. That's why we also wanted to explore. We wanted to explore it both ways, both space-time and initial data. Okay, so that is all. Here are the references from the slides. Thank you very much. Any questions and comments? Thank you.
Thank you. So we're a little bit over time. So if I might actually have to leave the room, but I can stop the recording and leave it for a discussion. Is there any question for Victor? Or quick comment?
Or comment, yes.
Yeah, I mean there were